Let's come back to our favorite geostrophic adjustment problem in the low latitude ocean. Again, assuming something like an aquaplanet with no horizontal pressure gradient, we can write our governing equations in zonal and meridional direction as we did before. And we can solve this, write this as d squared v dt squared plus f squared v by using this relation between v and u through these equations, where we can write the zonal and meridional currents in terms of the initial speed, which is the magnitude of u squared u0 squared plus v0 squared square root. So that's v0 cosine and v0 sine with negative sign here. Obviously, density is not an issue here. We can do the calculation we did before for the inertial circles, which I already showed once, and I said these are hard to detect in the atmosphere because atmosphere moves so fast and so many things are happening, whereas in the interior ocean it is much more quiet, and the surface winds, which can kick off a motion deep enough below the in the thermocline, can create these very observable inertial circles as we saw before. This is from the Baltic Sea. This is days going from 18 to 24 with a period of about 0.6 day, which corresponds to the Coriolis at that latitude and the buoy's depth at 14 meters. So that's pretty close to the surface, essentially in the mixed layer, slightly away from the direct wind forcing, so frictional effects don't kill away the inertial circles. Going now for the geostrophic adjustment problem, let's start with the shallow barotropic fluid of depth h, and we had the Rossby radius of deformation defined as c over f, where c of course is the speed of the gravity wave, so square root g h over f. The immediate problem is, what is h for the ocean? Obviously ocean is order 1 kilometer deep, and if you take g and put in 1 kilometer here, you get gravity wave speed of something like 100 meter per second, which is quite fast, and such a speed of this order does occur when there are tsunamis. As I mentioned earlier, tsunami is a shallow water wave, which means its wavelength is so large that L over 2, it's order 100 kilometers, so L over 2 is 50 kilometer, and the depth of the ocean is never 50 kilometers, which means the tsunami always feels the bottom, and it's a shallow water wave. But other than that, you have speeds that are order a meter per second for gravity waves and much lower for the Rossby waves. What is the issue there? Essentially, the ocean, because of its strong mixed layer at the top and the thermocline that isolates the surface ocean effectively from the deeper ocean, acts as a equivalent depth, which comes down to about order 100 meters. How do we think about it? Essentially, we define a reduced gravity, which I already mentioned earlier on. Of course, there is a mistake here again. It should be delta rho over rho 0 g. Remember, we wrote rho as rho 0, the background density, plus some perturbation delta rho. Delta rho obviously is much smaller than rho 0, and when you multiply g, the gravitational acceleration, with delta rho over rho, you get what is called reduced gravity. Essentially, if you think about two water columns, here there is no fluid above, and this is density rho 2, and you have delta that is related to the density difference. There is no fluid above. So in this case, the reference level between the two columns is this A and B, same as in this case where you have density rho 1 above. Here it's air, so you can assume the density of air to be basically 0 compared to the density of the water. And in A, rho 2 GH is what determines the pressure differential across this reference, whereas in this case the pressure difference is related to rho 2 minus rho 1. Okay, here rho 2 minus rho 1 is just rho 2 because rho 1 is 0, air, or very small. So this is what we mean by reduced gravity. You can imagine that if you perturb the buoyancy of a fluid here or here, the effective pressure differential is going to depend on the density difference and not the absolute density. That's all. So we have already said that before. And that gives us much more realistic gravity waves. And the earliest observations of gravity waves, I think, go back to the 1960s, if I'm not mistaken, where people used the data that was available. In this case, this is from 9th December 2014 in the tropical Pacific, going from the NORPAX array here at 150 degree west, epochs array at about 115 degree west, and the North Isabella data from here. And what is being seen here is the travel of the signal from the starting here at NORPAX. So you can see that there is a bulge created here by something called the Westerly wind burst, which is a sudden wind anomaly of a certain scale with a certain speed. So let's say something like 8 meter per second that lasts for about 7 days and then it dies. So it acts like a perturbation and sets off a gravity wave that propagates eastward. And you can see that here is the signal measured here. After a few days or more than a month, actually, it's measured here at 110 west, and then after some more time, it's measured here at North Isabella. There is some local amplification happening here probably, or the islands are having an impact in terms of the amplitude of the eastward transport per unit width. About the equator in meter per second. Okay, so it's not current, it's transport because it's averaged over a certain depth. So this is essentially a equatorial Kelvin wave, which is a gravity wave, and you can see the speed is something like 2.52 meter per second from here to here, 2.43 meter per second here, 2.4 meter per second here. So obviously local winds and Doppler shifts and so on make a difference in the local speed. It's not constant, but this is now much more realistic for the equivalent depth that we assume above the thermocline. So essentially this is the geostrophic adjustment problem in the ocean, where you set off a perturbation by a wind burst which created a sea level anomaly, and the wave passes by, and you can actually derive the anomalies of currents or transports associated with the wave. So even though you are on the equator in the zonal direction, you can still have a geostrophic adjustment in this sense that people like Joel Picot have done a lot of work on. And obviously when we said f equals 0 is a singularity, it's not such a serious singularity. It can be overcome. Let's use this figure again now to extend our understanding of the low latitude ocean dynamics to including the Ekman pumping and the interior flows generated by that. So I hope you're getting the idea. Oceans are forced by the winds. There is also the heating and cooling which can drive motion, but for now, if we focus on the wind driven circulation, how exactly does the interior of the ocean get into motion because of the forcing at the surface? As we mentioned already, water cannot go out of the ocean, so W is 0 at the surface, and W is Ekman pumping at some depth where the impact of the winds disappear. So we have to somehow resolve the wind forcing and the associated current and transport distributions in this Ekman layer, and then understand how the interior ocean adjusts to this water being pumped into the interior because of Ekman forcing. In the ocean atmosphere dynamics course, there is a lot of details on this because the Marshall and Plum book uses this idea of Taylor column and how the Taylor column has to move as a rigid body parallel to the rotation axis given this Ekman pumping. Different arguments, different way of explaining the physics, but essentially the same thing. But because we are here in the tropical dynamics, we are not going to go into those details. Let me close this podcast here and then come to the equations of Sverdrup circulation in the next podcast, which is a very elegant solution that was developed by Harold Sverdrup in the 1940s. Beautiful solution.